Hello and welcome to episode 6 of Why the Universe is Quite Disappointing, Really. I had to suspend making these videos for a few weeks because I had things to deal with at work, like examination, marking and assessment and all that kind of thing, part and parcel of what it is to be working in a university. But now most of that is behind us, so I can resume my awe-inspiring videos about how disappointing everything really is. I thought I'd resume with a short program about gravity. Gravity actually turns out to be the most important of the four forces of nature for governing the evolution of the universe as a whole. When you think about gravity in astrophysics, though, you tend to think about really exciting things like black hole collapses or supernovae, very dramatic events like that. The point I want to get across in this video, however, is that gravity, despite the fact that it's the most important thing in cosmology, really, is actually extremely weak. And in what follows, I'm going to try and explain a little bit about the physics of exactly why you should think of gravity as such a weak thing. So let me explain in a little bit of detail why I argue that gravity is such a weak force. And the way we can do this is just by thinking about the form of Newton's universal law of gravitation, or law of universal gravitation, whichever way you want to put it. So this law basically says that if you have two masses, which I've denoted here by m1 and m2, separated by a distance r, then the gravitational force between them is proportional to the product of the masses and the square of the distance between them. In other words, it's an inverse square law. And that formula at the bottom there, the gravitational force Fg is big G, which is a constant, gravitational constant, Newton's gravitational constant, times m1, m2 over r squared. So in a sense, the constant G sort of tells you how strong the gravitational force is for fixed masses at a fixed distance. Now, you can look up big G, the gravitational constant, in a book of constants, physical constants, and you'll find that its value is about 6.67 times 10 to the minus 11. In SI units, that would be in Newton meters squared per kilogram squared. Okay, so that looks like a small number, 10 to the minus 11 or thereabouts, but that's a bit unfair because it depends on the system of units that we're using, kilograms and meters and something. If we chose a different system of units, then big G would come out to be a different number and it might look larger. So you can't just look at that number and say gravity is weak because it's a small number. It depends on the units that you're using. So let's do a fair comparison. And I'll do that by studying electrostatics. If you know any physics at all, you'll know that the electrostatic force between two bodies separated by a distance r is given by Coulomb's law. And that says that the force is equal to the product of the electric charges on the two particles divided by the square of the distance between them. The constant of proportionality here is written in a sort of funny way in the SI system unit. It's 1 over 4 pi epsilon naught r, or 1 over 4 pi epsilon naught rather. And but you can rewrite, just call that k, and then that equation looks very similar to Newton's law of gravitation. It's a constant times the product of two things divided by the square of the distance. So it's essentially the same kind of law, it's just the units are different. And it doesn't involve masses, but charges. So let's put these two things together. And we'll see we've got the gravitational force, which is G times product of masses, and the the electrostatic force, which is K times product of charges, both of them divided by the square of the distance. So now we have two very similar equations, and we can really compare like for like in a way that is completely independent of the sort of units that we use, because you'll notice both of these are inverse square laws. So if we take two particles of given masses and given charges at the same distance from each other, then work out the gravitational and the electrostatic forces, divide one by the other. There's no dependence on distance because they both depend on r squared. So the r dependence cancels. So let's just pick a couple of particles that we know about, and we've got the data in our table of physical constants and data. I'm just going to consider here the force between a proton and an electron at any distance, because it doesn't depend on the distance, and the electrostatic force. Now there's a subtlety here because gravity is always attractive between masses, whereas the electrostatic force can be either attractive for unlike charges or repulsive for like charges. So we have to choose oppositely charged particles to get an attractive force. So that's why I'm choosing a proton and an electron here. So all we have to do to work out the ratio of those gravitational forces and electrostatic forces is to divide the one by the other, and the r cancels, so we get g times the mass of a proton times the mass of an electron divided by, well, proton and electron both have the same electrical charge. It's 1e. Now, I'm not going to do all the working here. It's about time you did something for yourself. So I'll leave you to look up those numbers in a table of constants. But you'll find, if you do it right, that the ratio of the gravitation and electrical forces on protons and electrons is a few times 10 to the minus 40. So in a very real sense, independent of the units that are being used, the gravitational force is 10 to the 40 or thereabouts times weaker than the electrostatic force. So you're probably asking, you know, what if it's such a feeble thing, why is it so important in cosmology? It's the preeminent consideration in cosmology. We work with theories of gravity all the time, and they make a huge difference. Well, the reason why it's so important to consider gravity, despite its weakness, is the fact that there is only one kind of gravitational charge. Masses always attract each other. At least in Newton's theory, they do. Masses always attract each other, whereas electrostatic forces, electrostatic charges can be either positive or negative. And that means if you have a positive electrical charge, the negative charges tend to be attracted around it, and they screen that positive charge from other charges. So you end up with very localized neutral objects that don't exert long-range electrostatic forces. Think of atoms, for example. There's a nucleus in an atom with a strong positive charge, but it's surrounded by a cloud of electrons which screen that charge from the outside world. So there are no large-scale electrostatic forces from atoms, but atoms still exert gravity because the electrostatic force is screened away. All that's left is this very feeble but quite persistent long-range force due to gravity. And that's what controls the expansion of the universe. I'll say one more thing about the weakness of gravity, and that's that it relates to the time scale for the evolution of the universe in a very simple way. So here's a little sort of rule of thumb, which is very useful in astrophysics. If you take a uniform spherical distribution of mass, of density, rho, that gravitational forces will tend to cause that mass, that collection of mass, to collapse towards the center. And you may not know, but the time scale for that collapse to happen, in other words, for material on the edge to reach the center, it depends just on the density and Newton's gravitational constant. It doesn't depend on the radius. So it's just that you can construct a characteristic time scale for gravitational collapse based on just the gravitational constant and the density. So if you do this calculation for the sun, you'll find its density is quite high, despite the fact that the gravitational constant is quite low. This timescale turns out to be quite short. If there were nothing holding up the sun from collapse, it would collapse in about half an hour. That's quite dramatic. It's something you could watch on video all the way through, except you wouldn't survive watching it from Earth because the Earth wouldn't survive that process. However, the problem with the universe is that not only is big G a small number, but rho, the density of material in the universe, as I explained in the last talk, is very low as well. And that means the time scale is very, very, very long. We don't know the density particularly well, but we think the time scale for the gravitational collapse of the universe, collapse or expansion of the universe, evolution of the universe, let's put it that way, is about 10 billion years. So a consequence for cosmology of gravity being weak and the density being low is everything takes a very long time to happen. Billions of years. It's all very, very, very slow. So there you are. I've explained the gravity of the situation to you. The universe now is rather empty, and because the gravitational forces are rather weak, it takes a very long time for anything to happen. As a cosmologist, I'm interested in studying not only the universe as it is now, but how it was in the very beginning. And in the beginning, it was much more exciting, we think. The density was higher, so the timescale for things to happen was much shorter. As far as we know, the gravitational constant hasn't changed during the lifetime of the universe. We don't know for sure about that, but in most theories, we just keep the gravitational constant the same. But because of the relationship between the timescale and the density, a higher density universe actually evolves much more rapidly than a lower density one. So the universe was much more exciting and dynamic when it was younger and denser than it is now that it's getting on a bit, doesn't get to do anything so dramatic anymore. Just like me, really.